structural effect that we are going to see, which contributes to the stability of carboxylate anion, is inductive effect. Now what is this inductive effect? Now let's say that this is a carboxylate ion and it has a negative charge here. Now the stability of the carboxylate ion, depends on how the negative charge over here is stabilized. So if this negative charge is being pulled out from this, and let's say that there is some group here which can help in pulling this negative charge from this carboxylate ion, then we would say that this group G is helping in stabilizing the negative charge on the carboxylate. On the other hand, if there is another group, say P, which is actually not removing the negative charge or withdrawing the negative charge on the carboxylate, but rather it is giving more negative charge to the carboxylate, then it will contribute to instability of the carboxylate anion. Now this is what we have seen in inductive effect. So what is inductive effect? So so there are two types of inductive effect, right? So we have seen that in your lower class would have seen there is minus I effect and there is plus I effect. Now this minus I effect is very similar to group G, which withdraws electrons. So which withdraws electrons. Okay. Whereas the plus I effect, it actually contributes by donating electrons. So it is actually electron donating group. So donating electrons. So this is electron withdrawing group, whereas this is electron donating group. Now we have just refreshed our knowledge about what is inductive effect. So now let's look at how this effect contributes to the stability of acids or in the stability of carboxylate anion. Now let's look at these structures. Okay, so before we dwell into more discussion, let's look at some of the values of different carboxylic acids which are structurally similar but have certain groups, and we'll just noting down the pKa values, we'll come to know the effect of these groups on the acidity. Now let me just copy those structures here. Okay. Now let's compare the acidities. Now before we begin, let me just refresh this. So if a molecule is having, let's say for example 4 as the pKa, and if another molecule has a pKa of, let's say 1, we say that this is more acidic and this is less acidic. So basically what I wanted to say here is that higher the pKa value, lower the acidity. So higher the pKa value, lower the acidity. Lower the pKa value, higher is the acidity. Now let's look at these two structures. Now this is formic acid. Okay, so so these two groups are the same, but what actually differs is this. So you have a hydrogen here, whereas in the second one, which is acetic acid, you have a alkyl group. Now we all know that alkyl group is an electron releasing group or electron donating group, so it adds to the negative charge on the carboxylate anion. Whereas here hydrogen, which doesn't exhibit that effect, doesn't contribute to the negative charge on the carboxylate ion. So as a result, the pKa value, you can see that this has a lower pKa than this one. So that means this is a more acidic. So this is more acidic. So this is more acidic than acetic acid, which has an alkyl group. The same effect is also seen here. So here also you have instead of an methyl group, you have an ethyl group. So that there also you see that it also has increased acidity. Now what happens if we add an electron withdrawing group? Now you see that the moment we replace one of the hydrogens over here with a nitro group, which is a very strongly electron withdrawing group or which exhibits minus I effect. Please note that here alkyl is a plus I effect. Okay, group that contributes electrons to the carboxylate anion here. Now the moment you have a minus I effect due to this nitro, what it does is that it can actually pull this negative charge towards itself, right, towards the nitro group, and thereby it is able to stabilize this negative charge effectively. And you just look at the value of the pK here. You see that it has gone drastically from 4.71 to something like 1.68. That is huge. So that means this effect is really great, right? Now if we have a chlorine in place of nitro, now we know that chlorine is also an electron withdrawing group, but it's not as strong as nitro. So this is reflected in terms of the pK value as well. You see here that the pK value has increased a bit because the electron withdrawing nature of chlorine is much less than the nitro group. So let's look at both the effects of inductive due to inductive effect. So minus I effect. So minus I group, which are electron withdrawing substituents when present at alpha carbon. So when they are present at alpha carbon, would decrease the magnitude of negative charge in a carboxylate anion and hence increase its stability, thereby increasing the acidity. So let's say for example we have a carboxylate, and let's say there is a nitro group attached to the alpha carbon. Now this negative charge, so let me represent this in a hybrid form. So this negative charge is now withdrawn by the nitro group and thereby it's stabilizing, and this effect is called as minus I effect. So when you have a group which can exhibit minus I effect, it would decrease the magnitude of the negative charge on this. So it is able to stabilize by withdrawing the negative charge from here to this side. So that's how it is able to stabilize. So, and we also saw that the pK of this nitro acetic acid is the pK of this nitroacetic acid is somewhere close to 1.6 compared to acetic acid, which was around 4.7. So you see that there is a drastic difference just by replacing one of the hydrogen with nitro. Now we also saw that we also see that a plus I groups, that is electron donating substituents, when present at alpha carbon would increase the magnitude of negative charge in a carboxylate anion, hence decrease its stability, and therefore plus I groups would decrease the acidity of the acid. So we saw that compared to formic acid, where you have an H group here. So where you have an H group here, now the moment you add a plus I group, which is methyl group here, you see that there is a drastic effect. So this actually decreases the acidity, so which is reflected in terms of increased pKa value. Now, another important factor that we also need to consider is how closer is this electron withdrawing group to the carboxylate negative charge or the alpha carbon. Now, let's compare the acidity of um, different halo substituted butanoic acids. Now, another important factor is also the where these electron withdrawing groups are. Now, the farther the electron withdrawing groups from the carboxylate center, from the carboxylate where the negative charge is formed, actually decreases the minus I effect. So here you see that in structure 1, the carboxylate is at the alpha carbon, whereas in structure 2, the carboxylate is in the beta carbon. In structure 3, the carboxylate is in the gamma carbon. Now you see that as the chlorine moves away from the carboxylate, that is from alpha to beta to gamma, you see that the pKa value actually increases. That means its acidity is decreasing. The reason why this is happening is that the more farther you go away from the carboxylate, the more the less effective is the electron withdrawing ability of the electron withdrawing group. So the proximity of the electron withdrawing group is important in considering the acidity. So that's very important in considering the proximity of the electron withdrawing group is also important in considering the acidity. So the nearer the group to the carboxyl, the greater is the minus I effect and greater is the acidity.